All right, so more about potential today. Uh, First, I'm going to start with an example from the book just to demonstrate how you would go about solving for the potential given some continuous charge distribution. So in this example, we've got a ring of charge, and we are going to try to find the potential, the electric potential, at some location Z above the center of the charged ring. And so the basic idea here is that if we want to find the potential, we've got to evaluate this integral dq over r, and the r value there is the distance from our infinitesimal charge element dq to the location that we're evaluating. So in this picture, you can see we've got a ring of charge, and what we're going to do is we're going to break up the ring into tiny chunks, and we're going to add up all of the contributions from each of these little chunks as they contribute to the potential at this location up here. So how far away is that location P from the ring elements? Well, that distance r is just the square root of r squared, so that's the radius here, and then also z squared, the height. So this is going in for r. And then dq, the infinitesimal charge element, is just a little chunk of the ring. Well, how much charge is there? Well, it's lambda, the linear charge density, and then multiplied by how much of the ring we've taken a chunk of, and that's the arc length, so that's r d theta. And what we're going to integrate then around is theta, because we're just going to integrate from 0 to 2 pi all the way around the ring. And so when we look down here at the next integral, we've got our bounds from 0 to 2 pi. I've plugged in the lambda r d theta, and then I've plugged in for the little r value. And again, all of this stuff is just constant, so it comes out of the integral, and all you're integrating is d theta from 0 to 2 pi. And so that just gives you 2 pi. And then this gets rewritten here as q total, because q total should just be lambda multiplied by the full length of the ring, which is 2 pi r. And that's the final answer. All right. So the next thing we want to talk about is how to connect the electric potential to the electric field. I said in the previous video that the electric potential and the electric field are just two different ways to describe and to visualize and to conceptualize the distortion of space due to the presence of charges. All right, so now we want to look at connecting the electric field and the electric potential. So the first thing that we're going to point out is that if your electric field is uniform, then there's this nice relationship that you can use to talk about the magnitude of the electric field if you know the spacing of equipotential lines, or the change in potential over some small distance. So delta V here is the change in the electric potential. Delta S here is the perpendicular distance separating equipotential lines. All right, so in this case, it's just the magnitude of the electric field that I'm talking about, so the direction of the electric field. And this is really important, and this is a thing to pay attention to when you're looking at maps of equipotential lines, is that the direction of the electric field points towards lower potential, or pointing down the potential hill. So we're going to look at some examples of equal potential lines in just a moment, and you can immediately determine the direction of the electric field by looking at which direction is downhill, right? Which direction is towards lower electric potential. Now, this equation here is really only valid if the electric field is uniform. And so, in general, if the electric field is not uniform, instead of taking delta V over delta S, what we really need to do is take a derivative. And that's what I've got written down here. So this is, if you want to find the electric field from the potential, then what you really need to do is take the derivative of the potential with respect to x, and that's the x component of your electric field. And then, so that's this term. And then you'll also have a y component and a z component. Right, so it turns out that these three expressions are really just the calculus version of the expression there. Right, we've turned the deltas into derivatives. So to continue with this derivative, we can actually sort of describe and represent what's going on here in a more compact, in a more simplified manner. And to do that, we are going to define a new object called a vector operator. And I want to stress, don't get bogged down by the terminology here. Just make sure that you understand or appreciate sort of the basic math concept here, that this del operator, which we're defining as the derivative with respect to x in the x direction, the derivative with respect to y in the y direction, plus the derivative with respect to z in the z direction. So this is the Cartesian coordinate version of the del operator. Del acts on a function. That function could be a scalar, could be a vector. In this case, what we're looking at with the potential, we've got a scalar function, and so our del operator is going to act on our scalar function, the potential. So the gradient of a scalar function, and this is just any scalar function, so t just represents a scalar function, sort of like a placeholder. If you take the gradient of t, so that's what del, and then place the t value there, that's equal to taking the derivative of t with respect to x in the I hat direction, plus the derivative of t with respect to y in the j hat direction. And it looks like I forgot a plus sign. The derivative of t with respect to z in the k hat direction. And you'll notice that this is exactly the same thing that we have up here. We've taken the derivative of the potential with respect to x, with respect to y, with respect to z. And so what we've really done is we've taken the gradient of the potential, so down here, simplified it, we've taken the gradient of the potential, and that is essentially equal to the electric field. So gradient is basically the three-dimensional version of the derivative, right? So we're taking the derivative of this scalar function, but we're not just taking it in the x direction or the y direction or the z direction. We're taking that derivative in those three different directions. So the electric field is a vector. We need a way to find the components in all three directions, and this del operator, this gradient of the potential, is how we do that. So what I've written out is Cartesian coordinates, but of course you could also write out the del operator in cylindrical or spherical coordinates. And depending on the problem, the charge distribution or the potential may make more sense to be written in cylindrical or spherical coordinates. Let's say you have a line of charge, then cylindrical coordinates might make the most sense. And if you've got a sphere of charge, then spherical might make the most sense. All right, so now it's time to talk about how to visualize, how to represent the electric potential. And we're doing this primarily through equipotential lines. And so I mentioned this in the last video just towards the end. And so the first thing that we're going to look at is this this figure from the book where we've got a point charge. And so for a point charge, the magnitude of the electric field, some distance r away, is kq over r squared, and the potential is kq over r. So in this case, we already know what the electric field lines look like, and I've drawn them, or they've been drawn here, right, radiating out from the positive charge. And then I'll draw one arrow. So that's what the electric field lines look like. What did the equal potential lines look like? Well, since the potential only depends on r, the potential is going to be the same value all the way around a sphere, or in this case the projection, the circle, that has the radius r. And so that means these circles, the potential is the exact same value, whatever that value is, right? That would depend on what r is and what q is. But whatever that value is, it's the same everywhere on that circle or that sphere. Now, this next figure, we've got two charges rather than just a single charge. And so no longer are the equal potential lines going to be circles. And that's because now we've got two contributions to the electric potential. Right, if we want to find the potential at any location in space, let's say this spot right here, what's the value for the potential there? Well, then I have to figure out the contribution to the potential due to the negative charge and also due to the positive charge. And so since the potential, the calculation is slightly more complicated, right? You need to add up two terms. Then the locations where the potential is the same value are the locations where the sum of this expression, right, equals the same thing. And so when you do that, let's get rid of those lines. So when you do that, then you end up with equal potential lines that have a different spacing in different regions of the diagram. And so if you go around these surfaces, then the potential is not changing. But again, you'll notice they are no longer spherical, or in this projection, circular. You'll also notice that the electric field lines are drawn in here. And again, the same thing as before. So field lines going from the positive to the negative. And we're going to just zoom in on one of these lines over here. And you'll notice that these field lines are, of course, curving. And they're curving in such a way that every time we cross a field line and an equal potential line, the angles at which those two lines are crossing is 90 degrees. And you can really see that with this horizontal electric field line. But that's the case for all of the field lines that are drawn. And so this is actually what we're going to be doing next week in lab. We are going to be mapping out on this side. We are going to be mapping out the potential values over some area where there's source charges. So we're going to map out what the potential looks like, and we're going to essentially connect regions that have the same potential value. So we're essentially going to draw equal potential contours. And from those contours, we can immediately then figure out what the electric field lines must look like in that region of space, because the field lines must terminate at negative charges, and the field lines must cross the equal potential lines at 90 degrees. And so you can immediately go from this picture on the left to adding in those the electric field lines to get a better representation of the distortion of space that's been created by these two, in this case, negative source charges. Right, so that's next week's lab. Okay, so the last thing that we have to talk about for this chapter, focused on electric potential energy and electric potential, is the relationship between the electric potential and conductors and conducting surfaces. So to touch on this, I've got the figure here from the book where I've got a charged conducting sphere, and I want to consider, all right, what's the electric field produced by this conducting sphere? Well, using Gauss's law, the electric field is just 1 over 4 pi epsilon naught, Q enclosed over r squared in the r hat direction. And what this means is that I get an electric field of 0 inside the charged sphere, because the charges are all on the perimeter of all on the exterior surface, and the electric field outside the sphere behaves and looks like the electric field due to a point charge Q located at the center of the sphere. Right, and so this we've seen. What about the potential? Well, the potential is related to the electric field, right? Taking the derivative, essentially, of the electric field over the path length will give you the potential. So what that means is that the potential outside, again, this is similar to what we just said, the potential outside the sphere looks and behaves like the potential due to a point charge Q located at the center of the sphere. And inside the sphere, the potential is not 0, even though the electric field is 0. The potential is a constant value, right? When you take the derivative of the potential, you get the electric field. The derivative of a constant value, any constant value, will give you 0. So the question is, what constant value is the potential equal to? Well, the potential is continuous at the surface. So that means as you go from outside to inside the sphere, the potential value as you cross the surface has to be the same inside and on the surface. And on the surface, the potential is just 1 over 4 pi epsilon naught Q over the radius of the sphere. And so that's what the constant value inside the sphere is. It's not 0. It's this non-zero value depending on the charge Q and the radius r. The last thing that we want to talk about is what happens when conductors are in contact with each other. So here I've got two spheres. I've got a smaller sphere with radius r2 and a larger sphere with radius r1, and they are in contact by this wire. So when conductors are in contact, we can treat the entire extended surface as one surface, and what that means is that the potential at both of those surfaces has to be exactly the same. And so I've got two spheres here, so I'm writing out, all right, well, this I know is the potential at the surface of sphere 2 and the surface of sphere 1. And so those 4 pi epsilon naughts cancel, and you get that Q2 over R2 has got to be equal to the ratio Q1 over R1. Well, R2 is smaller than R1, so that means Q2 has to be smaller than Q1. So there's more charge on sphere 1 in this case, right? Larger sphere, more charge. But remember that charge is related to sigma, the surface charge density, multiplied by the entire surface area. And so even though there's more charge on sphere 1, if you plug in this expression, you end up getting that sigma 2 times r2 is equal to sigma 1 times r1. And this means that even though sphere 1 has more charge, sphere 2 has the higher surface charge density. And so this is in general true that the smaller radius of curvature your surface has, the higher the surface charge density is. And so what this means is that if you have a surface that has non-uniform curvature, let's say it looks something like this, well then more charge is going to build up in this region than in this region. And that's because the radius of curvature in this region is much, much smaller than the radius of curvature out here in this region. Right, and so this has significant practical applications. We've talked about this in class, but this is essentially the principle that the lightning rod is built on, where you've got this sharp point where then charge will accumulate, the charge density there will be the highest, and then you can have discharge from clouds or from the charge buildup of clouds in the air. So you get strikes to your lightning rod, which is grounded, rather than to your home or whatever building or object you're trying to protect. And so that is the end of Chapter 7. And for the next class, we're going to be, or for the next video, we're going to be moving into some applications of these electric topics, and we're going to be talking about capacitors.